Alright, hello, my name is Brett, and today we're going to be talking a while about bonding and molecular forces. There's a lot to go over here. We're going to cover a lot of different topics with bonding and molecular forces, but we're going to do it a bit slowly. We're going to get through it thoroughly and do it right. So this might take a little while, but it's going to be worth it, especially for beginners and people taking elementary chemistry. Alright, so we're going to do this in 3 parts. In the first part, we're going to talk about the prerequisites for bonding and molecular forces. So basically, the parts in chemistry that you must know, and a bit of a review to go over what goes into these, what we have to consider before we start talking about these forces. Part 2, we're going to be talking about the intramolecular forces. This is usually what you would learn first in an elementary chemistry class. And of course, if you know your Greek and Latin roots, intra, within, so within a molecule. So those are the forces keeping a molecule together. And then finally, we're going to talk about intermolecular forces, inter meaning between. So in that, we're going to be talking about what keeps one particle attached to another particle. All right. So the first thing in part 1, here are the topics we're going to go over. We're going to go over the thing that has so many different names: the electron shells, clouds, energy levels, however you want to say it. Basically, the different layers and regions that electrons lie in, and from that we're going to talk about what a valence electron is and how to find them. Those are super important for bonding. We're going to see then how valence electrons will determine the ionic charges on a molecule, and then after we talk about molecular charge, we're going to talk about how those charges have a tendency in trend between metals and nonmetals. And then finally, we're going to extend that trend into talking about electronegativity. So all of these things, for the most part, you should have heard about already, but these are very important topics, so we're going to review them and look them over during this video, just to make sure you've got a good foundation to understand what we're talking about here today. And what we're really talking about here today, starting with part 2, is the intramolecular forces. And here are the main things we want to talk about with intramolecular forces. We're going to talk about ionic bonds, polar covalent bonds, and nonpolar covalent bonds. Those are the 3 main types of intramolecular bonds. We're not really going to talk about metallic bonds because those aren't super important or super well, they're common, but we don't really need to talk about them much. They're pretty simple. We're going to talk about the octet rule, which is heavily related with covalent bonding specifically. And ionic bonding. It's an all bonding. And then finally, we're also going to talk about partial charges, how those relate to polar and nonpolar covalent bonds. Then after we get through the intramolecular forces, we'll talk about intermolecular forces. And intermolecular forces, the main ones here, before we even talk about them, we have to talk about what a bond really means and how that relates to a molecular dipole. But really thinking about bonds as forces more so than just like some connection as an actual force, and then relating that to a molecular dipole. And then we'll actually talk about the different intermolecular bonds, those being the dipole-dipole attractions, the hydrogen bonds, which are a special case of dipole-dipole attractions, and then finally the London dispersion forces, which are within all, but are especially important for the nonpolar molecules, nonpolar covalent molecules that we learned about in part 2. That's why we learn about the intramolecular, because the intramolecular composition of a particle will determine what the intermolecular behavior of the molecule will be. All right, so let's get started with part 1, some of these prerequisites. So right off the bat, let's talk about these electron shells. Of course, you can go by any name: electron shells, energy levels, electron orbitals. Just don't go with the rings. This is a very generic, on the screen here, this is a very generic version of what is called a Bohr model. The Bohr model is when you have the nucleus in the middle, either represented by the protons and neutrons, as in this, or just represented by the letter of the molecule, and then the rings or shells or energy levels where the electrons will lie. Here is the Bohr model of neon, the second noble gas, so right after neon, right after helium. As you can see, neon is the 10th. It is 10th in the periodic table, periodic number 10. So it'll have 10 protons in its nucleus, and then you can see if you count there are 10 electrons on the rings around it. And here, the Bohr model can be quite confusing. Here's an example of Einsteinium, the 99th element. The reason I chose Einsteinium in particular is because you'd have to be Einstein himself to make any sense out of this molecule. The only thing I can really figure out from this Bohr model is that it looks a lot like the autopilot from Wall-E. But going beyond that, seeing this graph of Einsteinium can kind of show you some of the limitations of the Bohr model, because when you get to really big particles, at some point it becomes increasingly difficult to get much information about them. And as you can imagine, that these Bohr models don't actually represent what a molecule will look like, because obviously these electrons don't just run on these straight tracks around around the nucleus. There's no rings per se, as you might see in one of these Bohr diagrams. They're useful simple models of the molecule, but what molecules actually look like and these electron shells actually look like are better represented as orbitals. So orbitals, if you've done electron configuration at all, you'll be familiar with the s, p, d, and f orbitals. When you're filling out those charts and filling out the electrons into these orbitals represent general regions where electrons will exist. By the Heisenberg uncertainty principle, it is impossible for us to know both where an electron is and where it's going at the same time. There's always going to be ambiguity there. So instead of being able to track their location, we're able to track a general region that we can expect them to be, and that's what these orbitals are. That's why you also hear the term electron cloud, because it's generally a cloud area region about where we can expect them to be. So the s orbital is this kind of, oh, by the way, these are, this is probably won't be specifically needed in your course. This is looking ahead a little bit, a bit more advanced, but this will, if you can you don't need to understand this completely, but try to wrap your head around this slightly so that you kind of understand the general idea of what a molecule actually looks like. So this s orbital is a large ball, spherical thing. These orbitals, the p orbitals, on the other hand, are kind of more in an hourglass shape. And then the d orbitals are even more weird, and f orbitals beyond that. Honestly, it doesn't really matter that much. There's good reason for them. So, as I was saying with electron configuration, I've got the electron configuration of neon in the bottom right there. See the 1s2, 2s2, and 2p6. 6 plus 2 plus 2 is 10. That's neon. Oh, neon is an atom, neutral. And you can see here, you can see the 1s and the 2s, the blue and the red balls, and then the 2p orbital, these hourglass shapes. So if you, how they work is in each one of these teardrop almost shape, orange shapes, is one electron. So you've got 1, 2, 3, 4, 5, 6, right? And then you've got 2 in each of these concentric spheres. So that's how you get your 10. So as you can see that in the electron configuration, these electron orbitals kind of stack on top of each other, and that's what forms the general cloud. And that's why the electrons that orbit, they orbit so much farther away from the nucleus than you might actually think. Also important to note that these electron orbitals aren't physical objects; they're just general regions. So don't be confused about overlapping or anything like that, because it is just an area of where it could be. So, as you might remember from electron configuration, there's the s, p, d, and f block, and we can see those here too represented as the orbitals for the s, p, d, and f. If you notice, so the 1s is this sphere here, and then the 2s, it shows the white sphere around the blue sphere. That blue sphere is the 1s, and then the 3s's around the 2s's around the 1s, etc. So you can really see that as you get these bigger molecules, they just stack on top of each other. I think this diagram is super helpful to help understand what these look like and how they stack on top of each other to make bigger and bigger molecules. In fact, it's really elegant how this works, and it's really interesting. Like even with something like this 3D orbital, where you have the ring and the two teardrops, how it builds on top of it just like that. It's really quite elegant. And then overall, what does this look like when you have a bit more of a complex molecule? This is the quantum model of a molecule. by coloring the different electron orbitals. In the middle, those are the very dense d orbitals, and then you have two s orbitals and the p orbitals are the spheres in those same hourglass shapes that we saw earlier. So what do you notice about this molecule? What you should notice immediately is that the d orbitals are really small and clustered together near the center, while these s and p orbitals in comparison are gigantic. They're really, really big. And that's why in the electron configuration, well, I should say electron configuration, that's why the s and p orbitals will always exist as what we call valence electrons. So valence electrons are the electrons on the outermost layer of the atom. And as you see here, even though that you add the d ones later in the electron configuration, the s and p orbitals are just straight up bigger, so that they are actually more farther out than the d orbitals, even though you add the d orbitals in later. So if you're ever confused why that was an electron configuration, that's why. All right. So a valence electron, we have neon here. Neon is a noble gas, which means it's very stable, and the reason why that is because it has 8 valence electrons, which is a full energy level of them. This is according to the octet rule. The octet rule states that that a stable full energy level of valence electrons has the number 8, because that's 2 from the s orbital and 6 from the p orbitals, right? That in electron configuration, that's something you would see, that there was 6 in the p, 2 in the s, and that's a total of 8. So on the outermost layer, which are the valence electrons, it's most stable when there are 8. That's the octet rule, and we'll get to that later because that's super important. So neon, neon is a noble gas, so it's super stable, and as you would expect, it's got 8 valence electrons. So even with Einsteinium, which is a super confusing, huge molecule, the Bohr model still allows us to track the valence electrons. So seeing on the outermost ring, there are in fact 2 valence electrons. So even the Bohr model does help us find valence electrons, which is really, really great. But that doesn't mean we need to. That doesn't mean that we don't need to draw the Bohr model just to be able to see what the valence electrons are. In fact, there's a really, really nifty way for a really nifty trick that allows us to figure out what the valence electrons are for any molecule with around an atomic number 20 or below, basically before the d orbitals. So the way it works is we have our group numbers 1 through 18, but a more traditional way to label them actually is the A group and the B group. The A group being the S and P blocks, while the B group being the D block, the transition metals. So if you take the S and P blocks and do 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, as you see here on the chart, what you actually see is in front of the A is how many valence electrons you'll actually have. So if you see neon right here, 8A, 8 valence electrons, just as we would suspect. In class, when you're trying to figure this out, this is absolutely the best way to figure out how many valence electrons the element you're dealing with has. It's a really nifty trick. It doesn't work with transition metals, but that's okay. And Einsteinium, of course, is down here in the f orbitals, so it doesn't work with that either. All right, so something else we can learn about valence electrons is something called ionic charge, or molecular charge. There's a few different names for this as well. So the charge of a molecule is effectively the difference between its valence electrons and the most stable state of 8 valence electrons according to the octet rule. So how close is your element from having a full outer shell of valence electrons? Well, neon has a full outer shell because it's got 8 valence electrons from earlier, so it's going to have 0 charge. Whereas magnesium is going to have 2 plus 2 charge. I should say, don't be confused here. I say ionic charge, but that's not to say that magnesium as itself will normally exist as a +2. That would be a magnesium +2 ion. Magnesium as itself will have, what is it, 12? Yeah, 12 protons and 12 electrons in a stable state, so it'll have a net charge of 0. We're just saying that there's 2 valence electrons, so it's have as a +2, all right? That's the most important takeaway. Try not to get confused here with the idea of an ion, because this is not a magnesium ion yet, but when this magnesium does become an ion, it will have a +2 charge. That's because it has the 2 valence electrons. Then we have fluorine. Fluorine has 7, 1, 2, 3, 4, 5, 6, 7, but a full is 8, so it's missing 1. So instead of saying +7, we would say -1, because it's much easier for the fluorine to just gain an extra electron than it is to get rid of all 7, to either empty out or fill its shell. Oh, I didn't mention that with the magnesium one. I probably should have. So with the magnesium, the most stable state is when there's 8 in total, right? According to the octet rule. So magnesium has 2 choices. It's got 2 valence electrons on its outermost shell. So it can either go ahead and add 6 more electrons to get that 8, or it could simply take away these 2 on the outside, and then the valence electrons actually become the next level below it, the second level here. And if you see, the second level already has 8, so that's in a stable state. So that's why it'll rather get rid of the 2, because it's easier to get rid of 2 than take on 6. So when it takes away 2, the valence electrons drop to the next level, and that's a stable state, because there's 8 on the second level down there. Fluorine, on the other hand, is more traditional, because it'll just take an extra 1 to get to 8, because it's got 7 at the moment. All right, so there's some pretty nifty trends with ionic charge, with these ionic charge, right? So we saw fluorine. Fluorine's a -1. However, all the other halogens will also have -1. So that's chlorine, bromine, and iodine. Whereas the alkali metals, will be typically +1, alkali earth metals +2. Noble gas is always 0 because they're already full. And the trends continue. Notice this big purple block here. That's when the trend doesn't really apply. So don't worry about that as much. But these are very common elements that you'll be dealing with. So knowing these general trends of the -1, -2, -3, 0, +1, +2, especially these 6, is super helpful for you, and will speed up your process when dealing with valence electrons and ionic charges. So in accordance to those, I kind of spoiled this a second ago, but in accordance with those ionic charges, metals and nonmetals have trends. Metals, metals typically are positively charged, while nonmetals are typically negatively charged, right? That's what we see here. The nonmetals usually have negative. See negative here, besides the noble gases, they're neutral. So these are all negative. Well, these were all positive. And then, of course, transition metals are weird and we don't talk about them. So the alkali metals, the alkali earth metals, noble gases, halogens, they all have their trends. The idea of a metal versus non-metal, we won't go into what makes a metal versus a non-metal here. That's something that you learn at the very beginning of chemistry. But note that different bonds will occur between metals and non-metals. All right. And speaking of, I should mention that this is actually a really, really nice graph for a bunch of different information. I'll probably leave the link to this in the description, in fact, because I just really like this periodic table specifically a lot, especially for beginners who's not familiar with these trends. Being able to see what an alkali metal is, where the earth metals are, the lanthanoids, the actinoids, transition metals, poor metals, that doesn't show the metalloids, but the noble gases as well. It doesn't show halogens either, which is weird, but also the solid, liquid, gas, and unknown state at standard temperature, standard conditions. This is a great table, so I'm going to link it. I thought it was worth even making it large enough to break my aesthetic layout because of how much I like it. All right, so one more thing in the prerequisites is electronegativity. Electronegativity, as you know it, you may never have exactly been taught what electronegativity is, and really what it is the greediness of one of these elements. It's how greedy is this element for um, to become stable again. If you see these, the noble gases, for the most part, they don't really have any electronegativity because they're already stable. Krypton and xenon are a bit more reactive, so they're an exception. Um, and then radon just goes off the charts. Um, this is a bonkers element. So something like fluorine that only needs one. The halogens only need one. Um, so the idea is how greedy is it? How much does it want to get that extra electron onto it so that it can become stable? How much does it want to become stable? And something that's super important is that electronegativity scales with the size of, or it scales inversely with the size of the element. So the smallest molecules will have the highest electronegativity. And this makes sense because when they're all really clustered, it's very high levels of attraction within the molecule. So it's gonna have a much greater pull to get electrons together. That's why fluorine has the highest and francium has the lowest. Something else to know about electronegativity, just like atomic weight, is that these are all calculated experimentally. So if these numbers don't line up with what you've seen elsewhere, don't worry about that at all. There's huge variance. This is one of the few charts where I've seen fluorine be below a 4.0. Usually you see fluorine 4.0 or higher. It doesn't really matter because these are experimental and they're always within a decently close range. So something that's important about electronegativity that we'll get to in a second is their electronegative difference between two elements will determine what kind of bond occurs between them, but we'll get back to that later. But just remember that electronegativity is how greedy something is for the electrons, how much it cares about having the electrons towards them during the bond. All right, so then we're ready to start on part 2 and get into some intramolecular bonding. And no better place to start than with ionic bonds. These are usually the first ones you learn about because they're the simplest. Ionic bonds occur between metals and non-metals, and they create ions. They're called ionic bondings because it takes two neutral states and creates two ions from that. And remember, metal with non-metal. That's the best way when you're looking at a random bond to identify if it's ionic or otherwise, is if it's between a metal and a non-metal. All right, so the first ionic bond we're going to talk about is the most classic of them all, NaCl, sodium chloride or table salt. This is a super simple bond. It's an ionic bond, and it's probably the prime example for any ionic bond that you'll see. So this is what the bond looks like. It's an Na-Cl. The dash line here represents a bond. Simple enough. So what does this look like? Let's take a look at sodium and let's take a look at chlorine, the two components of this bond. Sodium, you can see, has one valence electron, while chlorine will have 7, right? 1, 2, 3, 4, 5, 6, 7. So this has one valence electron, this has 7. So what do you expect the behavior of these two molecules when they come into close contact with each other? The sodium is going to want to lose this one so that it can drop down its valence energy level to this one underneath it where it has 8 already, and that'll be stable. And the chlorine really wants the electron that the sodium has so that it can attach it to itself and bring the 7 up to an even 8, and that will also be stable. So that's exactly what's going to happen. The sodium, sorry for the blurry pictures, the sodium is going to transfer its electron to the chlorine, and now the outermost ring goes away for the sodium, and it drops down. The valence shell drops down to 2 energy levels instead of 3 energy levels. And there's 8 on the outermost, so it's happy. Then chlorine, it just got an extra one, so it's also happy because now there's 8. However, sodium, atomic atomic number 11, has 11 protons, However, now there are only 10 electrons. That means it has a +1 charge now. So now this, after the ionic bond, now Na is Na plus ion. So sodium becomes a positive ion, and similarly, chlorine is number 17, and now it has 18 electrons surrounding it. So it has more electrons than protons, so it's a -1 chlorine minus ion. So the chloride anion and the sodium cation. And that's what sodium chloride is. This ion, and then of course, because positive and negatives attract, these two are really close to each other, and they're stuck together in that bond in that sense. So let's look at this again. So before, Na had 11 protons and 11 electrons because it was neutral, and had one valence and an ionic charge of 0. Remember ionic charge, of course, these are neutral states, so they'll have 0 ionic charge. And then chlorine has 7 protons, 17 electrons, and 7 valence, and then an ionic charge of 0. This 7 and this 1 are both unstable, but 8 and 8 is very stable, or rather 0 and 8. So this transfer is going to happen. And then afterwards, the sodium now has 11 protons and 10 electrons because it gave one of its electrons to the chlorine. But now when it got rid of the third energy level, so it dropped down 1, and this smaller shell has 8, so there's 8 valence electrons now. And that has 11 minus 10 ionic charge +1. Whereas the chlorine got that electron from the sodium, so it has 17 protons, 18 electrons, and 8 valence electrons because it was at 7 and it got 1 more. However, 17 minus 18 is -1, so there's an ionic charge on the chlorine of -1. So that's why these are now ions. All right, so we'll talk about another ionic bond. This is very similar as well, calcium chloride, CaCl2. But this is between 1 calcium and 2 chlorines. So let's look at these molecules again. So calcium's a bit bigger than chlorine, but as we can see, calcium has 2 valence electrons and chlorine we know has 7. So calcium can't just dump both of its electrons onto the chlorine because chlorine only has space for 1 more electron and then it becomes stable. But if it only gives 1 to the chlorine, then the calcium will still have 1 valence electron and it's not stable. So what's actually going to happen is that 2 chlorine atoms are going to come to a single calcium, and the calcium is going to give one electron to each of the chlorine. And that way, the chlorine gets rid of both, so it's down and it's stable. And each of the chlorines are going to become stable because they each get their little electron themselves. So something to note here is that the calcium got rid of 2, so it's going to have 2 more protons than electrons. Well, each of the chlorines got 1, so these will be each -1. And if you think about it, this makes sense because +2 minus 1 equals 0, and you want there to be 0 change in charge. All right, so that's everything about ionic bonds. I hope this makes sense. We had 2 different examples here, one of which one was just between 2, and this one is between 1 and 2. All right, so then we'll move on to polar covalent bonds. So covalent bonds occur between 2 nonmetals. However, polar covalent bonds creates a polar partial charge, and we'll get to what that means in a bit. But so as ionic bonds occurred between a metal and a nonmetal, covalent bonds occur between 2 nonmetals. Okay, and there's 2 different types of covalent bonds, as we saw earlier. There's the polar and the nonpolar. If you're confused on what that means, think of what a polar is: the North Pole and the South Pole, polarity on a magnet with the positive and negative charges, exact same idea. What happens is that after this bond occurs, you have one side of the atom will have a positive charge and the other side will have a negative charge, and that creates a polarity, and that's why these are polar covalent bonds. If this doesn't happen and it's all balanced, then you have a nonpolar bond. We'll get to some examples that shows this. All right, so let's take a look at one of the most famous, of course, polar covalent bonds, dihydrogen monoxide, but you probably know it better as hydrogen hydroxide, of course. So hydrogen, very famously, has one proton and one electron, and that's all it needs, hydrogen. Whereas um, oxygen is 8, so it has 2 on the lower one and 6 valence electrons. So 1 valence electron on hydrogen and 6 valence electrons on oxygen. This isn't relevant, but funny story. Well, not story. If you take away this electron from the hydrogen, all you're left with is a proton. So it's very common in chemistry for the H plus ion. So when hydrogen has one less electron than it should, just to be called a proton. So again, hydrogen and oxygen 1 and 6. So just as we saw with CaCl2, since oxygen needs 2 and each hydrogen only has 1, 2 hydrogens are going to come together at the same time against the oxygen to fill in the 2 gaps. However, what happens here is because they're 2 nonmetals instead of a metal and a nonmetal, instead of the hydrogen sending one of its sending its only electron to the oxygen, it's going to share the electrons with the oxygen, and that's why you see the overlap in these circles here. So what these overlap means is that it's on both the hydrogen ring and the oxygen ring, so it's counting for both. So these are actually these are bonding together because they are actually using the same electrons to become stable. Of course, hydrogen is an exception to the valence, to the octet rule, because hydrogen is only at an energy level of 1, this innermost ring, and that can only hold 2 electrons anyways, so hydrogen is happy with only 2 electrons. That's hydrogen and helium are the only exceptions to that. They're happy with only 2. Where oxygen, of course, follows the octet rule, so it needs 8. So these are your lone pairs that are unbonded, whereas it takes one of its electrons and it shares it with the hydrogen, and it shares another one with the hydrogen. So the hydrogen has these 2, this hydrogen has these 2, so these are both happy, and then the oxygen has all 8 of these, so it's also happy. Everything here is stable, and that's what a covalent bond is. It's the sharing of these electrons between the oxygen and the hydrogens. All right. So something interesting here is, as you can see, all of the electrons are in this oxygen space. So it's all whereas of course the Bohr model is inaccurate and the electron isn't actually spinning around. Instead of the electron going all over the place around the hydrogen, it's sticking on the side towards the oxygen, and that's happening on both of these places here. So what's happening is all the electrons are clustering towards the oxygen here, and so you actually have like half an ion, if you want to think of it that way. You have a partial positive charge on these edges of the hydrogens, because there's not a uniform distribution of the electrons. They're all clustering towards the oxygen. So the oxygen has a partial negative charge, while the hydrogens have a partial positive charge, because the distribution of the electrons is uneven. They're all clustering towards this bottom side. They're all clustering towards the bottom side of the molecule, towards the oxygen. So because they're not even, there's a partial positive towards the top side in these empty spaces. Because then this proton is giving a positive charge all the way up here, but the electrons are always down here, so it's just a positive charge up here. It's not a full ionic charge, it's just a partial, and that's why we represent it with this lowercase Greek letter delta. That means partial charge. Not necessarily 1/2, 2/3, 1/3, anything like that, just partial. And we can assume that these partials are about equivalent to that negative. All right. So these partial charges are super important, and that's what makes this a polar covalent bond in opposed to a nonpolar covalent bond. The polar covalent bond has these partial charges because the electrons aren't distributed properly. The top side of the particle has positive charges, while the bottom side has a negative charge. All right. So if you think of it, you can kind of think of it as this is the positive side of the magnet, and this is the negative side. All right. So then we'll move on to nonpolar covalent bonds, and in nonpolar covalent bonds, this asymmetry will not occur. So there will be no polarity there. Probably the most basic most basic nonpolar covalent bond is carbon tetroxide, carbon tetra carbon tetroxide, better known as methane. And methane here is CH4, a carbon and 4 hydrogen. So let's look at these molecules. So of course hydrogen, the 1 and 1, it's going to have 1 valence electron, while carbon has 4 valence electrons. All right, carbon is molecule number 6. All right, so let's see how these will bond. So there's a carbon, and carbon is in the middle. It's 4. So what it could do is it could either drop 4 or it can gain 4. And you may think that's in the middle, but for some reason carbons really like to gain 4, just in general. And because it likes to gain 4, it's going to take on 4 hydrogens. Oh, let's show this anyways. Uh-oh. Let's try to reload. All right, let me get back to that slide. That was odd. Look at how many slides we've already gone through, everyone. Boom, boom, boom. All right, we did calcium chloride. We did hydrogen hydroxide. We've done methane. All right, here it is. This is what I was trying to show you. So this is going to take 4 hydrogens and a carbon in the middle. This is called a hydrocarbon because it's composed of only hydrogens and carbons. And as you can see, the hydrogen on each of here links with a carbon, and the carbon shares an electron with the hydrogen, so that the hydrogen has 2 in its ring and can be happy on each of these, whereas the carbon has 8 on its ring, so it's stable and happy as well. Again, we see the sharing of these electrons. I hope that at this point you kind of understand this idea of covalence, where they're sharing the electrons. The hydrogen is sharing its, the carbon is sharing its, and when they count for both, it looks like it turns out that the hydrogens are stable and the carbon is stable together. All right, so let's take a look at the partial charges here. Again, all the hydrogen electrons are clustering towards the carbon, so in the carbon you're going to have the negative charge because all of the electrons are clustered towards the carbon, and that leaves the partial charges on the outside near where the hydrogens are. That's what we saw in the hydrogen hydroxide. I'll just call it water. Fine, in the water from earlier. So in the methane here, we have a positive charge on all 4 of the hydrogens, and then a negative in the carbon in the middle. But what you'll notice is that since it's positive on every side, it's still perfectly balanced. There's no polarity there. On the outside it's positive, on the inside it's negative. So there's no positive and negative end because each end is positive. It's just that the inside is negative. So that's why it's nonpolar. If another particle came up to this one, if another particle came up to this one, it couldn't find a different poles on the particle because everything's positive on the outside. Oh, and I should remind you that even though we're dealing with 2D models here, of course molecules exist in 3D shape in 3D space. We're not going to cover VSEPR or molecular geometry or bond angles in this lecture, but remember that this will have like a tetrahedral shape, this hydrocarbon methane. So it's going to have like a pyramidal shape where these are all on the outside like a pyramid. And so at every point of that pyramid, it's going to be giving out a positive partial charge, so there is no polarity. It's all the same charge on the outside, so it's nonpolar. And that's the core idea of a nonpolar covalent bond. And that differs from the polar covalent bond because in the polar covalent bond there was that asymmetry. One side had the negative, the other had the positive. So that'll lead. We'll talk about this more in part 3 because that asymmetry versus symmetry has massive effects on the intermolecular relations. But before that, we have to talk about breaking the octet rule. The octet rule is something really, really nice that we love to use because it helps us find. It's a rule of thumb that we just need to find 8 for anything that isn't hydrogen, and it'll be happy. Unfortunately, that's not the case sometimes. Sometimes what ends up happening is that like with xenon, it actually has 12 this covalent bond has 12 around the center. Why this happens? Basically, there's just there's more electrons that it knows what to do with, but it is a reaction that happens. These are just things that happen sometimes because, it's science and it's nature, and things are never as pretty as we would like it to be all the time. So this is just a reality that we have to face sometimes. Luckily, it's pretty easy to identify. If it's something like xenon fluoride, or what is that? Xenon pentafluoride, right? Um, where it's ZeF5 or BrF5, F4, something like that. It's easy. Typically, it's pretty easy to identify. But when you actually start counting your valence electrons and trying to distribute them about the xenon and the fluorines, you'll find out that you have to break the octet rule sometimes, and that's okay. So if that does end up happening, don't think that you did something wrong. It's just a reality in nature that sometimes the octet rule is broken, and this mostly occurs with elements beyond atomic number 20. So if it's beyond atomic number 20, we're more likely to break the octet rule, but below number 20, and so 20 and below, you should be fine. But so xenon is way above 20, so the fact that it breaks the octet rule is not super surprising. All right, so then we can move on to part 3, intermolecular forces. And before we talk about them, we have to talk about these things called dipoles. And the central idea of a dipole is that we have to shift our thinking a little bit. So as before, we've been thinking of these bonds as connectives, connections between two molecules, either the ions coming together from the electron transfer or them just sharing. However, bonds are also attractive forces that are keeping these particles together. And that's why the attractive forces, right? So what we'll end up with are we'll have these attractive forces we could represent as force vectors. If you've done anything with engineering or vectors in math or in physics, you'll be familiar with vectors, how to work with vectors. If you're not, that's okay. This will be where you learn it. It's pretty simple. So there's bond dipoles and molecular dipoles. So if the bond dipole is the force vector, then the molecular dipole is the net force vector. It's the total vector where you add up all of the force vectors to see the result. This might sound confusing, but it's actually pretty simple. So let's look at water, the dipoles on the water. So the water molecule had the positive partials on the hydrogen side and the negative partial charge on the oxygen side. So the bond dipoles that we put in yellow, they look like that. We put them along the direction of the bonds, from the hydrogen to the oxygen. So we know the hydrogen is the positive side and the oxygen is the negative side. So we make a plus sign at the back of the arrow to show the positive side, and then we point the arrow towards the negative side, the oxygen, and that's the direction of the vector. The vector is directed in the direction of the arrowhead. Likewise, this bond is going down to the left because that's the direction from the positive to the negative along the bond angle. And then to find the molecular dipole, we add together the two bond dipoles, the two bond force vectors, and what we see is that this one is heading up somewhat and this one is heading down somewhat. So the overall, when you add these together, the up and down cancel each other out. However, this is to the left, and this is to the left as well partially, because this is going up and to the left, down and to the left. Since they're both going to the left, the overall molecular dipole is going to be a force vector in the left direction. I hope that makes sense. And that kind of reflects what we saw here, because the positives are on the right, the negatives on the left. So overall, you're going to have a positive right side and a negative left side on the molecular dipole. So yep, the molecular dipole represents the overall polarity of a molecule. So remember, the water was polar covalent, and that's why there's a molecular dipole in that direction. Now let's look at methane. So methane, if you remember, had the pluses on the outside and the negative in the middle. So if we do the same thing with the dipoles, bond dipoles, along the direction of the bonds, from the positive to the negative, what we see is something a bit different. The H from here goes to carbon, the negative, going up, but this one goes down. So these two are going to completely cancel each other out. And similarly, these two are going to completely cancel each other out. And then all of a sudden, there's none or negligible molecular dipole whatsoever, because everything is self-contained and cancels each other out. And that reflects what we saw earlier, where there's positives on all sides, so there's no polarity. And that's why this is a non-polar molecule. There's no overall molecular dipole because all of the force vectors cancel each other out within the molecule. There is no molecular dipole on nonpolar molecules because of this canceling out. And that shows a greater symmetry between among the structure of this hydrocarbon compared to that of water, because these are like all angular and they don't kind of cancel out, whereas these are nice and straight against each other, so they do cancel out. So that's the idea of a dipole, bond dipole, and molecular dipole. The molecular dipoles are what's important for the intermolecular forces, because molecular dipoles will determine how they interact with other things, and what kind of bonds they form with other molecules. So the first, we'll talk about when there is a molecular dipole in the case of a polar covalent bond. And that's when we get dipole-dipole attraction. And so these occur among polar molecules. So that means there's a non-zero dipole moment. Dipole moment's another word for molecular dipole. So what happens here is we have the plus side of the molecule and then a negative side of the molecule, and then another molecule with a plus and negative side. And these two will come together because the negative side will attract to the positive side. So what does that look like with the water from earlier? If there's two waters next to each other, the positive side here is going to attract to the negative side here of another water molecule, and they're going to come together front to back like that. The negative side is going to attract with a positive side. All right. I hope that makes sense. That's basically all there is to dipole attraction. It's pretty simple. When there's a molecular dipole, then one side's negative, one side's positive. So when these molecules come together, if a positive side meets a negative side, they will bond together, and that's a dipole attraction, dipole bond. Then there's a special case of dipole attraction, which occurs namely with water. It's called a hydrogen bond, and that's when there's a dipole attraction between hydrogen and one of the following: fluorine, oxygen, or nitrogen. Exclusively and specifically these three molecules. So one of the best examples is water with itself. So the positive side of the hydrogen and the negative side of the oxygen, they're going to come together. They're going to attract like this. The oxygen chew one of the hydrogens. And hydrogen bonds are especially strong versions of the dipole bonds. Hydrogen bonds are very, very strong, and that's why the surface tension of water is so great. That's why you can put so much water on a penny, creating this huge dome before it explodes. It's because water uses hydrogen bonds, which are very strong. And that's also why water is so good at dissolving stuff. All right, so here's a diagram that helped me learn this. H to the F, O, and N. There's a bunch of different fun heuristics that you can use. One of my favorite ones I learned from my chemistry class is that Harry got the phone, something like that. H to the FON, hydrogen bonding with an F, O, or N intermolecularly is a hydrogen bond. Very strong. So ionic bonds are the strongest, then hydrogen bonds, then these polar covalent bonds, which are the general case back here. Let me repeat myself. Ionic bonds are the strongest, then hydrogen bonds, then dipole, general bonds, and then finally the weakest are London dispersion forces. London dispersion forces are my favorite because I think they're so incredibly cool. It's such an interesting phenomenon. So it should be said that London dispersion forces actually occur among all molecules that just exists. It occurs everywhere. However, they're so weak that it's more they're most important in non-polar particles specifically, because in a polar particle, the molecular dipole, the dipole moment, has such a greater attraction um, that the London dispersion forces are nearly negligible, especially for smaller molecules. However, when there's a nonpolar particle, there is no molecular dipole, so London dispersion forces are the only thing keeping them together intermolecularly. Intermolecularly. Um, I'll explain how it works in a second. Something to note is that these scale greatly with the size and weight of the molecule. So the bigger the molecule, the greater these dispersion forces will be. So the way they work is they induce dipole moments on other particles. So imagine this: you have these molecules roaming around in space, right? Within a substance, say a solution. So that's a bad example, not a solution. So you have a molecule, and in the molecule, there's all these electrons floating around, okay? However, these electrons are moving quite randomly, and they're moving all over the place. So, sporadically, temporarily, because all the electrons are moving around so fast, what might happen is that the electrons there won't be evenly distributed. A lot of electrons might gather to one side of the particle and create a slight partial charge on one side of the molecule from the other for a short transient time. And in that time, there's a slight molecular dipole because of that uneven distribution of electrons. That's how slight these things are. The electrons moving within the molecule might move in a way so that it makes a slightly uneven polarity, and because there's that uneven polarity, that pole will move the electrons in the next molecule over. So that's the induced dipole. I think I have a picture of that here. Yeah, so there's an uneven distribution of electrons, and so from that creates that dipole creates a force that on the next particle over induces a dipole because it shoves the electrons in that next nonpolar farther away from it, which creates a dipole within that. And by the time that this induced dipole is created, this one the temporary one has already gone away. That's how fast it is. However, by the time this has gone away, the damage has already been done because the electrons that pushed and induced the dipole on the neighboring molecule will have already created a chain where the fact that this next one got pushed and set uneven, that creates a new dipole that pushes the next one over, which pushes the next one over, next one, and soon enough, these London dispersion forces create um, um, a bond between these nonpolar molecules that otherwise wouldn't bond together because they're nonpolar. There's no molecular dipole moment, but just because electrons move randomly, this can happen. As you can imagine, these are very weak bonds, and that's why a lot of nonpolar molecules, if you think methane, is typically a gas at room temperature because the bonds between them are so slight that it's very uncommon for them to be able to hold together. Other hydrocarbons like methane that are also nonpolar, think of propane, octane, those are very similar. Hexane, which you might have done with any sort of solubility. The bonds are really weak in nonpolar because they depend on London dispersion forces, so they have to exist as a gas. Existing as a liquid, they evaporate very quickly because the bonds deteriorate rapidly. Because all they use are these London dispersion forces. And that's also why it scales greatly with size and weight of the molecule. The size and the weight of the molecule, if it's a really big molecule with a ton of electrons, when you induce that dipole moment, that means you're shifting more electrons, which creates a greater difference in charge. Um, and if it's a bigger molecule, then the molecules are further away, so that means they get pushed further. So as you can imagine, there's more, they're being pushed further, so that creates a bigger force. So with really big molecules, these dispersion forces can be quite significant, actually. But But that's everything. We covered everything that has to do with intermolecular, intramolecular, and also the prerequisites to learn about this. I hope this was helpful for you guys. If you have any questions and you know me, message me. Um, there's a lot here, so if you don't get it immediately, that's okay. But I hope now you get a better grasp of conceptually what a ionic bond is, what a covalent bond is, what a dipole-dipole bond is, what a London dispersion force is, what a hydrogen bond is. If you can understand what those are, you're much better off than most of the population in terms of scientific and especially chemical understanding of the universe. This is small, really nitty-gritty stuff. Um, a lot of this is quite complicated, and you're learning it at an elementary level where not all of your questions can be answered because the answers are really, really advanced, things that I definitely don't know about. Um, Today, some things that we didn't talk about in this lecture that you'll have to do in class. We didn't talk about molecular geometry, like the Vesper model. I mentioned that earlier. We didn't talk about bond angles, which goes hand in hand with molecular geometry. We also didn't do any examples of trying to create and structure Lewis dot structures. We saw a few Lewis dot structures earlier. Those are class activities typically. Usually you do a lot of practice with those, so I decided to leave that off these presentations. But I'm thinking I might do some more videos doing a few examples of Lewis dot structures. I'm not sure yet. But that's everything I have here, so I hope it really helped you. All right, thanks.